Okay, let's dive in. Measuring distances out there in space. It's uh it's a fundamental challenge, isn't it?
Oh, absolutely. I mean, think about it. You can't just use a measuring tape.
Right. And for ages, really, we could only directly measure the distances to stars pretty close by, our immediate neighborhood, basically.
Exactly. We're talking maybe a few dozen parsecs. Beyond that, you needed different tricks.
Which is where this idea of the cosmic distance ladder comes in. Sounds grand.
It is pretty clever, yeah. It's like building steps. You measure the distance to something close,
Okay.
use that knowledge to figure out the distance to something a bit farther away, and you just keep building outwards, rung by rung.
And a really important rung on that ladder, or maybe several rungs, involve these things called open
That's
clusters.
right. Open clusters were crucial. They're basically big families of stars.
Families. How so?
Well, they're groups, maybe hundreds, sometimes thousands of stars, that all form together from the same giant cloud of gas and dust, a molecular cloud.
So they're siblings, sort of.
Pretty much. And because they're born together, they have roughly the same age and the same starting chemical mix.
And these are still forming, like right now.
Yep, the process is ongoing in our galaxy. We see these stellar nurseries making new clusters.
That's pretty cool. And some we can even see without a telescope.
Definitely. You've probably seen the Pleiades, the Seven Sisters. That's a classic open cluster.
Uh-huh.
It's about 130 parsecs away. Then there's the Hyades, a bit closer, maybe 45 parsecs, and Alpha Persei, further out around 175 parsecs. All naked eye objects if you've got dark skies.
And because they have that shared origin story, same age, same stuff, they're super useful for astronomers.
Incredibly useful. It makes studying how stars evolve much easier. It's like having a controlled experiment. You know the age, you know the composition, so you can figure out other things like distance, how they're moving.
Yeah.
Much easier than for some random isolated star out there.
So born together, age together, stick together.
Well, for a while, they are bound by gravity initially, but open clusters are relatively loose cannons, gravitationally speaking.
Okay. Over hundreds of millions, maybe billions of years, they tend to drift apart.
What breaks them up?
A few things. The gas they formed from gets blown away by the hot young stars, which reduces the cluster's gravity. Plus, stars inside jostle each other, and the whole cluster feels tidal forces from the galaxy itself.
So they eventually disperse. Do they just vanish?
Not quite. The stars often keep moving in roughly the same direction for a while, even after the main cluster dissolves. We call those moving groups.
Fascinating. And you said these clusters, like Pleiades and Hyades, were key for that distance ladder, for reaching even further out. How did that work?
One big technique was main sequence fitting. You plot stars on a chart based on their brightness and temperature. That's the Hertzsprung-Russell diagram, the HR diagram.
Right, I've heard of that. Shows stellar evolution stages.
Exactly. Most stars fall on a band called the main sequence. If you know the distance to a nearby cluster like the Hyades, you can plot its main sequence. Then you look at a more distant cluster.
Plot its stars and see how much fainter its main sequence appears. By shifting the distant cluster's sequence vertically on the chart until it lines up with the nearby one.
The amount you shift tells you how much farther away it is.
Precisely. And some clusters also contain special stars called Cepheid variables.
Ah, the standard candles.
You got it. These stars pulsate, and the time they take to pulse is directly linked to their true brightness, their intrinsic luminosity.
So if you know how bright they really are, and you measure how bright they look,
You calculate the distance. By calibrating this period luminosity relationship using Cepheids in clusters where we already knew the distance, like from main sequence fitting.
we could then use Cepheids to measure distances to really far away galaxies.
Exactly. They became fundamental tools for cosmology.
Okay, so these clusters were like cosmic benchmarks. And our mission today, this deep dive, is really zeroing in on one specific famous cluster, the Pleiades.
That's the plan. The Pleiades, or M45 if you prefer catalog names.
Visible to the naked eye, famously beautiful. Seems like its distance should be straightforward, right? About 130 parsecs, you said.
Well, that's where the story gets interesting. For a long time, yeah, the consensus based on those indirect methods, main sequence fitting, etc., put it around 130, maybe 135 parsecs. It seemed pretty solid.
Okay. Famous last words in science, maybe.
Could be. Because then came Hipparcos.
Like the Hipparcos satellite. That was a big deal for measuring star positions, wasn't it? Launched in '89.
A huge deal. Its whole mission was astrometry measuring positions, motions, and especially parallax, which gives direct distance measurement.
Parallax. That's the thing where a nearby star seems to shift against the background as Earth orbits the sun.
Exactly that. Like holding your finger out and closing one eye, then the other. Your finger jumps against the background. Hipparcos measured those tiny angular shifts for over 100,000 stars with unprecedented accuracy from space, away from Earth's blurry atmosphere.
So everyone expected Hipparcos to just nail the Pleiades distance, confirm the 130-ish parsec.
That was the expectation. But when the results came out in 1997, big surprise.
What did it find?
Hipparcos measured the average parallax for the Pleiades stars, and the distance it implied was significantly shorter, only about 118 parsecs.
Whoa, 118. That's
Ah.
quite a bit closer.
Yeah.
Like 10% closer than everyone thought.
Around that, yeah. Maybe a bit less, but significantly different. It caused a real stir in the astronomical community. Here you have this state-of-the-art space mission contradicting decades of ground-based work and other methods.
So what happened? Did everyone just say, okay, Hipparcos is right, textbooks need rewriting?
Oh no, not at all. It sparked a huge amount of debate and new research. People immediately started looking for ways to check the Hipparcos result using completely different, independent methods.
Like what?
All sorts. People used optical interferometry, combining light from multiple telescopes to study a binary star within the Pleiades called Atlas, getting a direct distance estimate that way. Others used infrared observations from main sequence fitting, which is less affected by dust. Even the Hubble Space Telescope got involved, using its fine guidance sensors, which can make incredibly precise position measurements. And another technique, very long baseline interferometry, VLBI, using radio telescopes spread across Earth.
Wow, pulling out all the stops. And what did these other methods find?
Consistently, they disagreed with Hipparcos. They all pointed back towards the older, larger distance, somewhere in that 130 to 135 parsec range.
So the plot thickens. Hipparcos says one thing, pretty much everything else says another. Did they ever recheck the Hipparcos data itself?
They did. There was a major reanalysis of the raw Hipparcos data published about 10 years later.
Did it fix it?
It nudged the Hipparcos distance for the Pleiades slightly further out, maybe to around 120 parsecs. So a little closer to the consensus, but still significantly shorter. The discrepancy basically remained.
Okay, so we have this nagging mystery hanging around for years. Enter Gaia.
Enter Gaia, the successor to Hipparcos, launched by the European Space Agency in 2013. Designed to do astrometry, but on a vastly bigger scale and with much, much higher precision. We're talking measurements for over 1 billion stars.
1 billion. Okay, so Gaia looks at the Pleiades. What does it find?
Well, the very first Gaia data release, DR1, came out in 2016. It included something called the TGAS solution, which combined early Gaia data with older measurements.
Then there's
Analyzing about 150 Pleiades members in TGAS gave a distance of 133.7 parsecs, plus or minus a very small amount.
back towards the old number.
Exactly.
Oh.
A strong hint that the pre-Hipparcos consensus was probably right after all.
And Gaia kept observing, releasing more data.
Oh, yes. Gaia Data Release 2, or DR2, in 2018 was a game changer. Way more stars, way better precision. Several independent teams jumped on the DR2 data for the Pleiades.
What did they find? Was it consistent?
Remarkably consistent. One study looked at over 1,500 confirmed Pleiades members and got 136.2 parsecs. Another group did a really careful job identifying almost 1,250 true members and landed on 135.15 parsecs.
That's incredibly close agreement.
It is, and they even found evidence of stars escaping the cluster in a long stream. Yet another analysis of DR2 came in at 136.7 parsecs.
So it sounds like Gaia really settled it. The distance is around 136 parsecs.
That's the overwhelming consensus now, yes. All the high-precision Gaia results, analyzed by different groups using different techniques, converge beautifully around 135 to 136 parsecs. It lines up perfectly with all those other non-Hipparcos measurements, too.
Which makes the Hipparcos result look like the definite outlier.
It really does seem that way. The weight of evidence is now firmly against that shorter 120 parsec distance.
So looking back, any idea why Hipparcos might have gotten it wrong for the Pleiades specifically?
It's likely a combination of factors. First, measuring the parallax for something 135 parsecs away is hard. The angle is tiny, about 7.4 milliarc seconds. That was pushing the limits of what Hipparcos could accurately measure, maybe right at the edge of its 10% accuracy goal for many stars.
Okay, so it was just really difficult technically.
Right. And second, the Pleiades is relatively compact on the sky. The stars are quite close together. Hipparcos' observing strategy and instrument design might have struggled a bit with resolving and measuring such closely packed stars accurately at that particular distance. It wasn't necessarily optimized for dense clusters like that.
So a tough target that exposed some limitations.
That seems the most plausible explanation, yeah.
There's a kind of irony here, isn't there? You mentioned how crucial the Pleiades and Hyades were for calibrating Cepheids and building the whole distance ladder to galaxies. But now, Gaia is so precise and measures distances so far out directly using parallax. These nearby clusters aren't really needed for that specific job anymore.
That's a really great point. It's kind of amazing. Gaia's reach with parallax is so vast now, it can measure distances directly way beyond where we needed cluster main sequence fitting or even Cepheids calibrated in nearby clusters.
So a century of clever, painstaking work building that ladder step by step.
Has almost been leapfrogged by this incredible technological jump with Gaia. These clusters that were absolutely fundamental anchors are no longer essential bottlenecks for the cosmological distance scale itself. It really shows how far we've come.
Wow. So while the Pleiades might have lost its starring role on the biggest cosmic stage,
Its story is still fantastic. It highlights how science works, questioning results, refining measurements, the impact of new technology, and open clusters themselves, still incredibly important.
for understanding stars themselves.
Exactly. They're perfect labs for studying stellar evolution, how star systems form and behave dynamically. There's still tons to learn from them.
And I guess fully understanding exactly what went wrong with the Hipparcos measurement for the Pleiades would still be a nice puzzle piece to find.
It would provide some satisfying closure, definitely. Though the main question of the distance seems pretty well resolved now, thanks to Gaia.
So for you listening, just think about that. A measurement that seemed settled, that got thrown into chaos by new tech, then got resettled by even newer tech. Makes you wonder, doesn't it?
Mm.
How many other scientific facts that we rely on today might shift or get completely overturned as our tools get better and our data gets deeper? What current certainties might look different a few decades from now?
It's a humbling thought. Science is always a work in progress.
Definitely something to ponder.